We will now move on to the talks that are associated with the awards. The awards themselves will be given out tonight at the gala dinner. Right now we are giving both award recipients an opportunity to reflect on their work and their contributions to this community. We'll start off here with the presentation from the recipients of the 10-year Most Influential Paper Award. And for that purpose, I would like to ask Dimitris to come up on stage, please.
Right. Hello, everyone, and thank you for coming to this session. I know it's always hard after lunch. It is a great honor and pleasure to be here 10 years after I published my first models paper back in 2006 in Genoa. And it is a privilege to be here and to be delivering this talk in front of you. Right, so the organizers asked us to reflect on the work we published back then, and then to also update the community on progress that we've made in this direction. So it has indeed been quite some time, since 2006. I was a PhD student back then, much more handsome and taller. But seriously, preparing for this talk has given me an opportunity to think about my research over the last decade, and also to kind of trace it back eventually to this very work I will be talking about today. So it all started in 2004, 2 years before we submitted this paper to Models. I was just starting my PhD, and I was working for a new European project at that point, Modelware. At some point, the European Commission decided to ask projects to actually spend some time on creating logos, right? That's before that time. So this is a Word or something. Okay, but Modelware was a big project. It involved most of the heavyweights in MDE at that time, so Nantes, Braunschweig, Thales, France Telecom, and the like. And the work package I started working on had to do with model composition and merging. And after looking through the state of the art, the existing work on model merging and model comparison, we had this feeling that existing model merging approaches really targeted very specific scenarios where you had models that were homogeneous. In some cases, they were children of a common ancestor. There was very little space for customization of the comparison or the merging logic. Maybe some of them were weight-based, but you couldn't customize them a lot. So my first attempt was to try to abuse ATL, right? And I tried that for quite a while, and then I figured out that, right, maybe I should stop doing that to ATL. But I was inspired by what ATL had achieved in the domain of model-to-model transformation, so we thought that it would be useful to investigate the usefulness of a domain-specific transformation language for model merging. So the equivalent of ATL for model-to-model transformation, or OCL for model-to-text transformation, or back in that time, a MOV script for model-to-text transformation. And what we wanted, what we were missing from existing solutions was, first of all, expressiveness. As I said, solutions at that point were hard to customize. both in terms of the matching and the merging logic. We wanted whatever we would come up with to be both metamodel and modeling technology independent. We didn't want to bind it to EMF or MDR or any other particular modeling technology. And we thought, since we're designing a new language, let's, think big. We would like to support merging heterogeneous models, right? And this might sound strange. Why would you want to merge two heterogeneous models? But I have an example that will hopefully convince you. Okay, so the way the whole project started, when we realized that what we wanted to build is a language, since we were using ATL, we were in the kind of OCL or OCL-like language camp. So we started with an OCL grammar that I got from the Antelar website. And then I started abusing the grammar and trying to make it look like the language I wanted. The bad thing was that I hadn't taken the compilers course at my first degree. I thought, am I ever going to need to develop a language? Well, guess again. So after doing this, the hard part, coming up with a grammar, then writing an interpreter for the AST was produced by the parser, was easy. And then one of the first things we did was to introduce this abstraction layer for different modeling technologies. So instead of, well, at that point, MDR was probably the most popular technology coming from Sun. But instead of going straight to MDR, we decided to have this layer in between. And I will talk about this layer more. And one of the first things, again, we did mainly because of usability reasons, I mean for our own sake, was to implement some Eclipse-based development tools, very basic stuff at that point, just an editor and a launch configuration. Okay, so that's where we were in 2004, 2005. So we had the Epsilon merging language, which is the language that I reported on in this paper, a connectivity layer that shields the language from its underlying meta-modeling frameworks, and an implementation of this layer just for one framework, plus some basic development tools. Right, so let's go back to one of the main aims of EML, which was to support heterogeneous merging, right? And here I have an example where on the one hand we have taxpayer records from a national tax authority, say the HMRC in the UK. Here we have a model that conforms to this meta model. So I should say that these are three meta models. These are three minimal one-class meta models, right? So we have a model that conforms to this meta model, and then we have one that comes from a country that has published the income of foreign residents in the country and has made that available to everyone. So what we want to do is we want to merge the records that the tax authority has, which where taxpayers have declared how much income they have received in this country over here, with the data coming from this country where it says how much income they have actually received, they have actually earned in this country. And we want to identify mismatches for obvious reasons like tax evasion, fraud, etc. And then we want to merge these two models into a third model, which contains a set of letters, a set of notifications that will be sent out to any people with significant discrepancies. Okay, so here are two examples of models. Here is the data held by the National Tax Authority. Here's the data in the list published by by the country. So we can observe 4 types of records, right? So we can see green records where we have a person from the UK with a tax ID of 234 that has declared an income of 7,000 euros or pounds or whatever. And then in the local data, so in the national taxman's data set, the same national insurance number 234 has declared the exact same amount. So we're good here, right? Nothing wrong. Now we have the case of tax ID 345, which also comes from the UK, that has earned 6,400 units of money, while they have declared only 4,600 units. And this could be a case of tax evasion, right? It could be a typo. It could be a convenient typo leading to tax evasion. Then we have someone that has declared 6,000, but has only earned 5,000, right? So we probably still want to notify them, but with slightly different text. And finally, we have the case of an entry that has declared a UK national insurance number that the taxman doesn't have. So this is fraud, right? This is a number that doesn't exist. Right. So now so the first thing we want to do is we want to identify matches between these two models, and the colors here show the matches we want to identify. Right. So I'm going to show you how we can do that with the merging language, with EML. The first step involves establishing correspondences between elements of the two models. The second step. In the second step, we merge matching models, and then in the third step, we can transform non-matching elements into something in the target model. So first of all, let's see how we can match. So EML supports 3 types of rules: match rules, merge rules, and transformation rules, which correspond to these 3 different steps. So match rules specify pairs of types of elements that should be matched. So here we are saying that we want to match every person against every taxpayer, so every record of the left model with every record of the right model. And the comparison logic, the comparison condition, is that the 2 IDs need to match. Plus, we're only interested in persons from the UK, right? So you can see here that while these 2 entries have the same tax ID, we're not interested about this one because here the country is US. We're only interested in UK in this particular example. Right. So this is how when we run this rule, we establish these matches, right? And then the next step is to specify what we want to do with these matches, what we want to do with pairs of matched elements, right? And what we want to do is, first of all, we don't want to do anything with pairs of matching records that have the same income, right? We don't want to bother the people that have whose actual income matches their declared income. So what we want to do is we want to create letters for everyone else, essentially. And if the person has declared more than they have actually earned, then they're the taxman's friend, right? Otherwise, we can just threaten them. And here's the condition where we compare the income and we set the text of the letter to an appropriate string. We also want to do things with elements that have not matched. right? So if we go back to this example, this element has not matched, right? We cannot find it in our local records. We still want to do something with it. And in order to handle these elements, we can include transformation rules that will be invoked for all elements that have not matched, right? All elements of this type that have not been matched to anything else in the other model. Again, here we are only interested in persons whose country is the UK, and it's a case of fraud, so we can set the appropriate text. Now, as we saw, an EML program consists of a number of different rules, different types of rules, so matching rules, merging rules, transformation rules. And if we take a step back, these are actually 3 different languages, right? They share a common expression language, a common imperative expression language, and they share also model connectivity facility, so they can run on the same kinds of models, but they could be useful in their own right. And indeed, this is 4 languages, right? Because this common expression language could be a standalone language in its own right. Okay, so this is where we were in 2004, 2005. Once we split out, once we extracted and made all these sub-languages independent, we got here. So this is the common expression language. This is a language for model comparison. Its purpose is to build correspondences between match elements, between model elements, and just leave them there. And then here's a transformation language, which again can be used in its own right, but can also be embedded in the merging language. So the merging language ended up being just the merge rules, which need some sort of match trace to operate on, and this can be acquired through the comparison language or through something different, something like EMF compare, for instance. And then the transformation rules can be embedded in merging specifications, but they can also run standalone. So in 2006, with the help of Jean Bezevin, who was leading the GMT incubator at the Eclipse modeling project, Epsilon joined GMT. And it actually took us quite a long time to graduate, so it took us 6 years until we reached version 1.0. That was in 2012, and we're now in version 1.3 with 1.4 coming up. So we roughly do 1 major release every year. Joining Eclipse, the Eclipse Foundation was a very good thing for Epsilon. It gave the languages of the platform a substantial boost in terms of adoption. So since 2008, we have had about 8,000 posts in the forum. We are aware of several places where Epsilon is used both to teach model-driven engineering and also to support model-driven development in industry. And I won't say names. There is a list of users, both in academia, industry, and in open source, with appropriate evidence on the website. Right. So now that we had sorted out model connectivity, we had a robust expression language, the next step was to obviously do more languages, right? More languages were easy. So the first target was model validation, and that's to a large extent due to my personal frustration with OCL, because I always felt that writing constraints with OCL was like, working with one hand tied behind your back. So I thought maybe we can do something better. And what EVL adds on top of OCL is support for human readable messages, right? What do you show the user if a constraint fails? Still no standard way to do this in OCL. Constraint dependencies, and also quick fixes. So sometimes when you have a constraint, when it fails, it's straightforward to fix it. IDs provide quick fixing capabilities. Why not provide this as a first class citizen in a validation language? So here, for example, I demonstrate. So this first constraint was to make sure that for all taxpayers, for all persons in the list, there is a corresponding tax ID in the National Tax Month's database. And for these persons, like that red entry in a few slides ago, this message is produced, an appropriate message is produced. Now here, in this second constraint, we want to also match the incomes declared and earned, but this doesn't make sense for persons for which we don't have data. So here we can specify in the guard of this constraint that we should only try to evaluate this constraint if this person already satisfies this previous constraint. So this is again something that plain OCL lacks. Moving on, the next language to develop was a model-to-text transformation language, and I guess its distinctive feature is that it includes a separate sub-language for rule-based template invocation. So this looks a lot like a model-to-model transformation language, but instead of having a target, which is a model element type, we actually specify the template and the target. And then we have a clean separation between the coordination logic and the actual templates. So this excerpt is from a code generator, from a fully working code generator that produces a mapping code between Java and MongoDB, so that one can interact with Java objects persisted automatically by MongoDB. And the reason I have it here is to demonstrate this nice feature that the model-to-text language of Epsilon provides, which is support for custom, for handwritten code within generated code, and the preservation of such code when upon regeneration. Okay, another language we developed building on top of EOL and the nice infrastructure provided by Epsilon was the Epsilon pattern language, which is a textual language for pattern matching. It also provides in-place transformation capabilities, so it can act like a graph transformation language. It can keep trying to match and reduce patterns until no more changes are made to the model. What's nice about EPL is that matches are exposed as a virtual model. So we can take the results of pattern matching and treat them as a model that we can use, say, in a model-to-text transformation or in model validation, and so on and so forth. So here, for example, we have a pattern called public field, which looks for combinations of class, field, setter, and getter methods that satisfy certain conditions. So we're actually looking for setters and getters of a field, right? Combinations of the setters and getters of a field. In this case, we can declare that field as public. Now, having run this pattern, we end up with a virtual model consisting of public field elements, which have a class property and the field property and the setter property and the getter property, which means that then we can treat the results of pattern matching as a model, and we can write constraints for them, and we can say, all right, for all instances of public field, which are all matches of the public field constraint, I want to check that the types, for example, of the field and the getter is the same. and then produce a message if they're not. Right, so this is how Epsilon looked like in 2004, 2005. This is how it looked in 2006. And this is how it looks now, right? So we've expanded both upwards with more languages, and also we've added support for a number of modeling technologies. So EMF came quite early, although it wasn't the first modeling technology we supported. Then spreadsheets, things like Argo UML and XML followed, and more recently we've been working a lot on adding support for commercial tools like Artisan Studio, which is very popular in the UK defense industry, but also tools like MetaEdit, for which we have a reasonably good first draft. Right, so reflecting on this work, EML was the first language, at least to my knowledge, that was tailored for model merging. And the contribution of the 2006 paper at Models, beyond presenting the language, was that it made the case for merging of non-homogeneous models, so heterogeneous models. And more importantly for us, EML was actually the starting point, the seed from which Epsilon grew. Now, on the downside, and I have been advised not to use red here, EML is a little bit too verbose for the most common model merging scenario, which is the merging homogeneous models. You still need to specify all the matching and the merging logic. But this can actually be generated to a large extent using higher order transformations from meta models. Interestingly, EML has turned out to be one of the least popular languages of Epsilon in practice. And we can tell that by looking at our forums and at how much interest there is about each language, which probably hints that, at least at this stage, there's not much need for complex model merging or merging of heterogeneous models. Right. So looking ahead, we're working on a number of things that apply to Epsilon and therefore also to EML. So incrementality is our top priority at this stage. We already have the science sorted out. We know how to do it. We have a fully working prototype for the model-to-text transformation language of Epsilon. Now we need to provide a robust implementation across the entire platform so that we can do things like incremental model validation and transformation and code generation. Improving the user experience is always a priority. I think we've done as well as we can so far, and the next step would actually be to turn the languages into statically typed so that we can provide support for code completion and refactoring and the like, all these nice facilities. In terms of integration, as Epsilon is becoming more mature and we're seeing more adoption from industry, we have a stronger motivation to integrate with proprietary formats and modeling tools. And then, as models grow, we are also looking at optimization, so how to escape from the naive iteration behavior, for example, of select in EOL, so that we can make use of indexes instead of having to go through large collections of model elements. And I think that's pretty much it. So this little number here is misleading. And I will be happy to take any questions you may have. Thank you.
You made a very good case for your work. I also liked how you made a case for compiler courses. Taking compiler courses in undergrad and open repositories, right? You said that you started with a grammar for OCL that you got from the Antler site, right?
Yeah, that was very helpful.
Yes. So these things are good to have.
Other questions for Dimitris? Expressions of enthusiasm.
Sorry, I don't think I can hear you.
What's the reason behind having several languages? It's not possible to have list languages. What the chances of
There's always a trade-off. Yes, some things, for example, since we developed the pattern language, some of the tasks EPL is good enough for them. So, for example, model merging could be done using EPL quite easily. This is something we have considered, actually. So at some point, we are thinking of dropping some of the languages we have developed, because we need, every now and then, you need to clean up. Not everything you think about eventually makes sense.
While you're thinking of more questions, the perennial question, what would you have done differently?
It's hard to say. Well, I would have taken that compiler's course, right? That would have saved me a lot of time. In terms of technologies, Epsilon predates Xtext. If we post-dated Xtext, then I would have liked to build Epsilon on top of Xtext from its first version. But this is actually something we are also considering doing.
Right now you're having a textual language. Are you looking forward to go graphical somewhere in future?
No.
And why is that?
Because these are programming languages. I mean, how would you specify complex conditions with boxes and arrows and the like? It wouldn't make sense. Maybe a hybrid notation where you specify like the top level rules in graphics and then have text in them to specify the actual conditions and the merging logic would make sense, but we haven't explored that direction at all.
From your experience in building a project in Eclipse, what would you, I mean, how satisfied are you with the process, and any things that could be done to make it more efficient from well, a technology development or a research point of view? And also, second question, I guess, is did it help to get any traction from the industrial side?
Yeah, so to answer your second question first, it did help. So one of the major problems when you're talking to industry, as you probably know, is first of all the credentials of your work, and then this worry about the future of the work. And since the early days, when we were saying to our industrial partners that, this is an Eclipse project now, this already earned us some cookie points. Now, 10 years down the line, you still get the question, is this thing a standard? But now you can say no, but it's been developed under Eclipse for 10 years. And that kind of almost has, that has a lot of weight. Now, in terms of the Eclipse process, I think it's very well tailored to research projects. There's this incubation process where you have a lot of freedom. Your product will be below version 1.0, and there will be a clear indication to the community that this project is in incubation mode. There's a lot of support from project management committees and senior people at Eclipse. I think it's a very good and at the same time disciplined environment to develop code, because, for instance, you cannot just use any sort of library you want. You have to stick with a particular license, and then you also have support there. So, yep.
A short question. Very short.
So I know that you talk about the fact that you thought it was positive, and you just repeated that, but one of the things that we often hear about the use of Eclipse for research projects and so on is the overhead, and that's often the reason why people decide in research context to say, well, let's develop our own internal research technologies as opposed to take the burden of learning the Eclipse environment and so on. What do you, I mean, just in short, because I know it could almost be a workshop, but what's your view on it?
Well, over the last 10 years, I have seen lots of attempts to essentially redevelop an ID, because you start small and then you need the problems view and then you need multiple editors and then you end up redeveloping your own ID, and it turns out to be terrible. So no, it's definitely worth the trouble to build on something like Eclipse.
Okay, time to move on. Dimitris, we thank you for your presentation. We thank you for submitting the paper 10 years ago. And of course, we thank the models reviewers at the time for accepting the paper.
Definitely. Thank you.